Okay, so I am actually recording this lecture for the second time. I actually recorded this before, and apparently my microphone did not work at all, and so I, you know, gave this lecture for 2 hours, only to find out that none of the audio came through. So, found out that this particular lecture is quite long, and so I might split this up into two sections and post them, and then I'll post the second section and sort of try to find a place to kind of break away. Um, but will do my best to reproduce the events of yesterday. So today, this lecture, for the second time, we're going to talk about machine learning again. We kind of covered some of these things in lecture one, and we're going to sort of re-explore them and talk about them at a sort of lower level, but not super low level. We'll get into that in the next few lectures as we start to actually build out these algorithms and things like that. And then we're also going to talk about the different kinds of machine learning, like unsupervised, supervised, and reinforcement learning, and then also kind of explore the different applications that we might be able to use for those things, and then also how that interacts and integrates with game development and some of the things that we can use with how we can maybe apply this to simulation as well. So with that, let's get to it. So we talked about this a little bit in lecture one. So what is machine learning? Well, machine learning is a study of a class of different kinds of algorithms that improve using experience. And this is done without the explicit programming done by programmers to achieve those kinds of improvements. In other words, this is not like I implemented a sorting algorithm and I put it into the wild, and I see in particular kinds of scenarios it doesn't perform as well as I'd like it to, and so then I kind of go back to the code and add a new component to the code base or handling a specific case in a more explicit fashion. That's not machine learning. That's human learning, because what we did is we made a thing and then we put it out into the wild, and then as a result, it didn't do as well as we thought it would, and then we go and we do this back. So machine learning algorithms are actually algorithms that do this automatically. They do that by way of improving by seeing experience. And this experience can either be in the form of a data set. So the machine learning algorithm is exposed to a data set piecemeal, and as it's exposed to more data, it becomes more generalized across that data. And so in the context of supervised learning, experience is defined as a data set, for example, and maybe that data set grows over time as well, and there's kind of techniques to deal with that. In the context of reinforcement learning, for example, experience is literally the episodic trajectory of reward states and actions that a particular AI agent is experiencing inside of a particular environment. And we'll talk more about this. There's a little bit of a sort of weird one here in the context of unsupervised learning. And in unsupervised learning, what we're doing is we're taking a look at data that's unstructured, and from that trying to extract a pattern. And so in this context, this machine learning kind of regime deals with improving over time that distribution. It's getting closer and closer and closer to representing the underlying distribution or the underlying structure of the data that we're presenting it with. And you can kind of take that as almost like a philosophical comment that over time an unsupervised learning algorithm will improve its understanding of the world in sort of a more generalized sense. So that's kind of cool. And unsupervised learning we'll talk about in this lecture as well. So with that, let's move on. Apparently, okay, that's no good. There we go. So we discussed this a bit in lecture one. Machine learning is actually a subset of artificial intelligence. And this is maybe kind of a surprise to a lot of people that AI and ML are technically two different things, that ML is really just a subset. So let's kind of talk about what AI is. And this list actually comes out of Marvin Minsky's really great paper, Steps Towards Artificial Intelligence, that goes all the way back to 1961. I highly encourage you all to read that one. It's older, but it talks about these things in a much more like novel and a very sort of systematic way. And it breaks down AI into sort of 5 different sort of areas. And the first one being search. So search is a kind of AI, task a thing that we need to do. And you can kind of think about search as everything is search, right? Ultimately, if we have a problem that we want to solve, then if in theory we knew all of the solutions to that problem, we can just search through all of those solutions to then come to the best solution that may maximize or minimize some set of criteria that we're looking to maximize or minimize. For example, in the case of a tic-tac-toe game, right? Tic-tac-toe is a sufficiently simple game where you could actually codify every single possible state that the game could have. So in the case of tic-tac-toe, you've got 3x3 cells, and each particular cell you can have 3 different states, be it empty, be it an X or an O. And so now you can kind of do the calculation that there are 9 to the power of 3 potential different states, or no, 3 to the power of 9. Yeah, 3 to the power of 9. Sorry, I know math. And that's a relatively small, right? If we simplify this down to more of a, say 3 times 3 is around 10, right? So it's almost like 10 to the power of 8. So you've got a reasonably small number of states that you have to kind of consider in a tic-tac-toe game, that you could actually calculate every possible trajectory through that state space and get to a determination of what might be the correct action to take given a set of criteria like we want to win. Now, as you get into checkers, the number of states kind of grows rapidly to a much larger number. I think it's like 10 to the power of 10, something like that. I don't remember. But still, checkers is a relatively, solvable game. We can actually deal with all of the potential states and kind of potentially search through all of the different states and all the different sort of trajectories through those states by way of what's called a game tree, if you're familiar with game trees, right? Because at any given turn of the game, the state can change in a sort of set number of ways. And the total number of states in that tree is a limited number, and it's finite that we can calculate. And that's actually something that we can sort of search through relatively reasonably. But what happens when that search space gets sort of intractably large? So even with a game like chess, I believe the number of states goes up to something in the order of like 10 to the 40, or even more than that. It might be even 10 to the 100 or something like that. I forget exactly what the number of states are, but I remember reading somewhere that to actually calculate every possible state and trajectory of the game of chess, you would need a computer that is not feasible to build given the matter in the universe or some stupid thing like that. In other words, chess is we can come up with every possible solution mathematically, but to actually search through all of those potential solutions is an intractable computational problem. And so we can do things like create and generate game trees and search through them and that kind of thing, but we can't do so in sort of a cohesive or complete fashion. And so search, while it is the path to greatness and whatever, that's exactly what we're doing with most AI things. We're trying to search through a potential solution space, isn't always so possible, right? Now, that kind of leads us to the next thing that artificial intelligence then tries to do, which is a solution, a way to optimize or to reduce the search space, is by way of pattern recognition. So for example, if we can do pattern recognition and I can recognize that in a particular set of scenarios, the most likely next thing to happen is this, based on some set of sort of rules, then now I basically don't need to search a significant portion of the state space. And actually, in a way, that's sort of what you're doing with a game tree, right? Because with a game tree, I don't need to consider every other state in the space because many of them will never happen if I know the rules of the game. Also, I know in particular scenarios and patterns that if I have this arrangement, then the next likely arrangement or the next thing that may happen may fit a set of patterns. And pattern recognition can go all the way to image classification, which we'll talk about during this lecture, and understanding for example, let's take away the game aspect of this and talk a little bit more about very, very high dimensional type of data, for example, images, right? How do you do that calculation? The number of potential pixel configurations in, say, a 32 by 32 pixel image is quite large, right? It's whatever your bit depth is to the power of the size of your image. It's quite large, and so it's pretty much impossible to then search through every possible image to then determine all of the potential images of cats. So what if we could instead pattern recognize certain features about images that suggest that this image would be a cat? And so now we can basically turn a very large set of dimensional data into a much more constrained set of data, which we can then sort of do a much more limited search on, for example. So it's a bit of a contrived example, but pattern recognition is the core aspect of what AI does, what AI needs to do to allow for the search to actually work. Now, that's all well and good. Say we know what the optimal path is, and say we have used pattern recognition to determine a more limited set of potential solutions. We actually have to plan our way. Say we know, okay, we have 10 steps, and at step 10 we need to be here, and we know what the steps need to be, but how do we navigate through those and connect them and deal with ambiguity and environmental factors and other things that may change? And so planning is the other thing that AI needs to do. It needs to sort of plan a set of actions, or it needs to plan a set of iterative steps or transformations or whatever to ultimately get you to your intended outcome. So in the case of search, for example, search just gives you your next likely thing that you want to do. Maybe search gives you a number of things, and then planning sort of fits them together. And in planning, for example, you see things like behavior trees or hierarchical task networks. There are a lot of different ways to go about planning, some of which do not involve machine learning at all. In fact, search and pattern recognition have many approaches, and many of which do not involve machine learning. So this kind of, again, really justifies the fact that ML is a subset of AI. It's just a way to accomplish certain aspects of AI. Now, learning is a core aspect of AI, and learning is machine learning. In the case of artificial intelligence learning is machine learning. So that is the subset that we always talk about. But learning kind of at a higher level, like we talked about in the last slide, is really about making something better given experience. So say you do something twice, the second time you might do it differently based on the time you did it before, based on the outcome of that. So you kind of have to understand, okay, this was our intention, this is where we want it to be, this is where we got to, here's the difference, and here's how we're going to adjust our algorithm to get closer to this thing that we're looking to do. I know that sounds like a very contrived example, but it's actually not that far away from how most machine learning algorithms work. So finally, induction. And induction is kind of a weird one, and I think one that has yet to really been shown too much with machine learning in particular. I don't know too much about induction in terms of its progress with artificial intelligence, although those of you who are interested in induction may want to look into Judea Pearl, which talks a lot about causal inference and sort of the ability to induce from a set of mathematical or statistical probabilities causal behavior. So induction essentially is this sort of subject of, well, it's day outside. It's outside. It's not nighttime. It's light, and so that means that the store will be open, and the store will be open means I can go buy a apple because I'm hungry. This sort of induction of things being true because other things are true, and the sort of rationalization of ideas or representations or behaviors based on information that we know. So where learning is kind of rejiggering our behavior or rejiggering our algorithm based on what has been learned by way of experience, induction is then taking that experience and taking what we know, our algorithms, our systems, and using them to infer things that we have not seen before by way of sort of this inductive reasoning. And again, I'm not an expert on induction in terms of artificial intelligence or machine learning, so if that's something that's of interest to you, please reach out to me, and I'm happy to do a more deep dive on that subject, because it's a very interesting one, certainly. So yeah, with that, let's move on. Why is my, okay, maybe not. Okay, I'm not sure why this is not working as well as it should, but here. There, all right, sorry, that's annoying. So as we mentioned, ML is a subset of artificial intelligence, and so quickly we want to touch on what deep learning is. And deep learning is dealing with sort of a certain set of algorithms that have multiple layers. So machine learning is a set of algorithms that sort of try to represent or transform information from one representation to another representation so that we can then use it for a variety of different tasks, as we'll talk about. One example of this kind of algorithm is the perceptron, which was also introduced by Marvin Minsky and Papper in 1969 in their book Perceptron. And the perceptron was largely sort of motivated by the biological neuron, as you can kind of see. And we're not going to talk too much about the biological underpinnings of machine learning in that. And by the way, if you're really interested, neural networks were originally proposed by Alan Turing with the unorganized machine back in his day, which is pretty exciting. So this idea is not so new, right? As soon as we started to look under microscopes and see these neurons that are communicating with one another through dendrites and axons and so on, it was kind of clear that this sort of organized behavior, this modular or compositional behavior, is sort of a fundamental building block of a lot of intelligent systems. And so Minsky and Papert tried to sort of formalize this in a mathematical model. And you can kind of see on the right here, the perceptron is essentially just a summation of these input values that are weighted by some kind of set of weights. And so this is what an individual neuron in a perceptron layer looks like. So you would have x1, x2, x3 multiplied respectively by W1, W2, and W3. The summation of that would then give you the value y. And often y would also be some kind of transformation of that. So in this case, it would be also, you could maybe apply a sigmoid or some kind of function to a nonlinear type of function, as we'll talk about at length when we go into sort of machine learning implementations down the line. So in a particular perceptron layer, in a perceptron, you don't have just one neuron, you have many. So you would have multiple outputs of y, and you would have many of these perceptrons kind of on top of each other, as you can see in the bottom, although this is a multi-layer, which we'll talk about in a moment. And so in this case, if you have multiple of these neurons, all the neurons all see the same x1, x2, x3 input values, but each neuron has an independent set of weights. And so in that sense, one layer, one of these perceptrons, could be represented simply by a matrix of these weights, where each row is a row of the respective W1, the weights for each one. So the first row would be W1, W2, W3 for the first neuron. The second row would be W1, W2, W3 for the second neuron, and so on and so forth for the number of neurons that you would have in a particular layer of perceptrons. So that's a single layer or a shallow perceptron. And so when we talk about deep learning, and we'll talk about how we actually train these things and what all this means in the next few lectures. So don't worry too much if you're not really kind of on top, understanding a lot of this stuff. And we'll talk about it even more so in this lecture in a minute. But the only difference between sort of this sort of shallow implementation and a deep learning algorithm is that we have multiple of these layers. So you can kind of see in the bottom right corner here, we would have multiple input perceptrons and then a hidden layer of perceptrons, and then that would all output to an output layer. And if you think about deep learning, usually we're dealing with networks like this that have multiple hidden layers. And in fact, one of the models we'll talk about in this lecture has upwards of 152 layers. And we may talk about this in a future lecture, and I'm happy to go deep on it because this is one of my personal interest areas. But one of the sort of fundamental things we're doing with machine learning is trying to approximate a very, very complicated function. So you can imagine, for example, taking a picture and determining whether or not it's a horse or not. So in a way, what we're trying to do is determine what's the probability distribution of a horse. How can we maximize images of horses going through our function thingy that would then give us a representation of a horse? And in that sense, we're trying to approximate the probability distribution function of a picture of a horse, which is a very, 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 very complicated function, right? I don't know even how you would write such a function, but we're going to sort of approximate it by way of these machine learning algorithms. And so there's a fundamental theorem, which is the universal approximation theorem, which says given one of these perceptrons of an arbitrarily, like an infinite width, meaning as many neurons as you can possibly imagine, you can approximate to an arbitrary degree any complex function. So this is also based on the Stone-Weierstrass theorem, which shows that it's a similar thing to kind of like a Fourier transform, but with polynomials, where you can basically approximate any complex function to an arbitrary degree given a sufficient number of polynomial terms, which is something you can do, by the way, with these perceptrons, the linear combination of which we'll talk about in the next lecture. And so it's really cool. More recently, it's actually been kind of a while. It took a bit for people to kind of prove it, but in the context of deep learning, it's also been shown that if you have a bound layer, so you don't have infinite neurons, but you have some number of neurons in a layer, and that number is dependent on your input data dimensionality. If you have an arbitrary depth, so an infinite depth of them, you can actually do the same thing, but you can kind of imagine that a bound depth, a bound width versus a bound depth is a much better thing to have, because in theory, you're going to get arbitrarily close based on every single layer that we add on to this stuff, which is an iterative process, whereas when we're doing an arbitrary width, we're multiplying many, many, many things all at once. It's like a sum, and so you can't. So the sum, an infinite sum, it takes infinitely long, whereas a infinitely deep algorithm is one that you can get kind of arbitrarily close to the end of, because you could just iterate on it every single time. So you can just make things better and better and better. You don't necessarily have to go all the way to the end until you get to arbitrarily close to where you want to be, which is represented usually by some kind of error, like an epsilon or something like that. So long story short, deep learning is essentially the dealing of machine learning algorithms which have multiple layers that are deep. So it's really kind of like a marketing term, and it still is just machine learning. Again, we're with this, so cool. So let's talk a little bit about the different approaches of ML and some of the applications. And as we'll go into these things, I'll talk about different models and different things that you can do with it, which you'll see are very exciting. And we're going to get to some shallow level of depth on the technical side with at least supervised learning in this lecture. But as we go into the future lectures, we'll actually start talking about building these things and implementing them. And keep in mind, right, this class is all about you guys, what you guys want to explore. Anything in this lecture is really kind of up for grabs if you want to do your topics presentation or your project on it. There's a lot of really great ideas here, and I'll call out things in particular. But if there's things that are not in here, this is not meant to be an exhaustive representation of the machine learning ecosystem. This space, even the things that I'm going to be talking about that are state-of-the-art, have only been developed in the last few years, and really kind of, as you'll see as I talk about supervised learning, the beginning of the sort of renaissance of ML started around 2012, which is not all that long ago. Even though some of these ideas go back to 1961 and 69, as I mentioned, in fact, up until recently, the state-of-the-art natural language processing approach, the LSTM, that was published in 1997. So a lot of these ideas are old. But what's changed is that we have the computational power, and we have the data sets, and also we have the theory and understanding. And all these things have kind of led to this really big explosion in machine learning research and things that you could do with machine learning and computers in general that up until recently people thought were out of reach, like classification, as we'll talk about, and even the generation of generating new data that doesn't exist, that a lot of people didn't believe was going to be possible. So we'll talk a lot about that in this lecture, which I'll try to split up kind of in a good place if I can. So there are three kind of main pillars of machine learning. One is supervised learning. And in supervised learning, you're dealing with data that has an underlying structure attached to it. So this could be, for example, a set of images, and each image is an image of a particular kind of object, and alongside each image we have the representative label of that image. So say you have a bunch of images of cats and dogs, and each image comes along with a piece of text that says this is a cat, this is a dog. As we'll see in kind of the case of computer vision applications, this ground truth, as it's called, may also include bounding boxes to show you where the dogs and the cats are, and in some cases what's called segmentation data, which shows you pixel for pixel where objects in the scene happen to be. So this is sky, and this is dog, and this is background, and so on. So supervised learning deals with data sets that have been supervised, meaning we know that the data, not only do we know what the data is, we also know what it represents, and the underlying structure is given to us. And that's the difference between unsupervised learning, where in unsupervised we're dealing with algorithms that try to pull a structure out of unstructured data. So in this case, unlike the last one, we would get a bunch of pictures of cats and dogs, but we wouldn't be told which is which. There would just be a bunch of pictures, and maybe you can look at it and say this is a dog and this is a cat. But the goal of unsupervised learning is to sort of take a bunch of data that we don't know much about and then pull from that sort of strategic or underlying structure. And this is very, very valuable for the purpose of generation. So if we can take a lot of data and then figure out what makes that data the data that it is, then we can, in theory, generate new data based on those rules or that probability distribution. And so this is kind of the underpinning theory of generative models, for example, which utilize exactly that. You figure out an underlying distribution, a probability distribution that represents your data, maybe a very complicated function. Again, we're approximating these using neural networks. And if you can do that, then you can just kind of plug in random inputs and then get, valid outputs. And this is kind of how a lot of generative models work. Another thing that unsupervised learning is used for is actually as a sort of, front end to supervised learning. So if we can do this and sort of come up with a bunch of different labels that maybe we don't know what the labels are. So I give you like 10 million images of a variety of different objects and so on. Your unsupervised learning algorithm can then figure out, oh, these objects are similar, right? And it doesn't know what the objects are, but it gives all of the objects that look like a plane an arbitrary value of 7, and it gives all the pictures of a dog an arbitrary value of 2. Then you plug that into a supervised learning algorithm to train it. And again, you don't know what these classifications are, but maybe we can kind of finagle this to a point. And this is, by the way, how like recommendation systems work, where or like news aggregation, where a news aggregation solution doesn't know what you're really looking at. We'll talk more about that in a moment. And then finally, reinforcement learning deals with, like we talked about, these agents and these environments that are trying to react and maximize a reward over a particular period of time steps. And so reinforcement learning uses both unsupervised and supervised learning. And this is something kind of that you'll hear a lot in this lecture, that these three sort of paradigms are not mutually independent. They work together. They are based on one another. You can do one using the other and vice versa. But they kind of are dissimilar in the sense that while they are learning something, they're learning a different thing, right? In supervised learning, you are learning how to match a particular kind of expected transformation. In unsupervised, you're trying to determine the underlying structure. And in reinforcement learning, you're trying to learn the optimal set of actions to take, or what's called a policy. So we'll go deeper into it as we go along. So in supervised learning, and we'll go much deeper into this in the next set of lectures. But with supervised learning, you're given a set of I examples of X and respective Ys for those. So that can kind of look like X1 and Y1, and this could be, for example, X could be a image and Y could be a classification. So say a dog or a cat or what have you. And you have a bunch of these, and then our goal is to create to determine a function that can then transform a particular input X in the space of X to the Y space. So say X is the space and the real number of like a pixel thing. And then Y is just a value, a real number that represents a class, say from 0 to 1,000, where each number represents a different object, say a dog or a cat or a plane or a house or what have you. And so this kind of adds a bit of a caveat. You have to think about this assumes that the data set that we provide our algorithm provides a sufficient underlying representation of the data on whole. So say we don't have every picture in the world, we don't have every piece of information, and so the function g that can transform from x to y is going to be only as good as the data that we use to determine it. And so this is a big sort of limitation and caveat for supervised learning, meaning you can't quite separate your algorithm from the data that was used to train or to determine it. But this is just something you should keep in your mind as you start to think about machine learning and what it can do and also what it can't do. But let's go back to this function g. You can kind of imagine like this function is probably pretty complicated. How do you create a function that can take a picture and tell you if it's a tree or not? Well, the reality is that function is probably exceptionally complicated. But go back to what we were talking about a little bit earlier about the ability of these networks and algorithms to sort of approximate an arbitrarily complicated function to an arbitrarily, accurate degree. And so what we do is we don't directly determine g, because that would be either intractable from a mathematical or an analytical standpoint, or maybe computational standpoint. But instead, what we do is we then, want to determine a function that, whoops, that's great. 1 second. Okay, I think we're back. Although, I'm going to have to do this way. Great, that's fine. Okay, so we're talking about, sorry about that. We're talking about the g function that we're approximating. And so the goal is to, approximate this function g. Because we can't directly calculate g, or it's intractable, or something else of that nature. And so what we can do then is we can try to do this with a perceptron, for example. And the way we're going to do that, this is the worst thing. Okay, let's now talk about the 1D, the one-dimensional aspect of this. And this is one of the utilizations of supervised learning is fitting data. And so one idea is we can kind of create this general model, and if you can think back to the perceptron, this is sort of that same kind of example, where we can create a model. We can just wave our hands around a lot and say, okay, our function approximator is going to be a linear affine transformation of our input data. So in this case, f of x is going to be equal to theta 0 times x 0. Actually, it's an error. It should be just theta 0. So in this case, x 0 doesn't exist. Or you can maybe add it. It's up to you, but it's like a bias term technically. But anyway, f of x is equal to theta 0 plus theta of 1 times x1 plus and so on and so forth until theta n of xn. And so our model is parameterized by this vector theta. And so our value f of x is simply a dot product of all of those values, plus x of 0 set to 1 in this case, and it's just the sum of all that. So it's just a dot product. So this is also what's known as a linear affine transformation. So if any of you have done graphics, you probably recognize this in terms of just a dot product. And if you have multiple neurons, in this case, like a multi-layer perceptron, a multi-perceptrons, you can see this as just a matrix multiplication. So that's why this choice is pretty common. But we're talking about the one-dimensional case where we have many, many parameters, and we just want to map that to some kind of continuous value. So you can imagine this being, for example, a housing data. So we want to determine the potential cost of a house based on its square footage, location, or a bunch of different features of that nature, where the output is just the value y, which is in the form of dollars, right? And so not only can we do this, we can also kind of combine these features into multiple features, and we can use sort of polynomials. So say our model, we don't want it to be a straight line, which was what we would see in the case of that model, but we also want to add maybe linear combinations of different polynomial aspects, so we can actually do that relatively easily. And so this is our model. Our model is this sort of set of features as defined by our data. And again, if this is too much, don't worry. We're going to really go into depth on this with like linear regression and logistic regression, this is literally linear regression. But if we have this system, this linear system, right, you can kind of think to yourself, well, this is something we can just solve directly. Like, why do we have to do all this learning nonsense? We can just directly determine our set of thetas by way of the normal equation method, because essentially if you take the above and you say y is equal to theta times our value x, then you can actually solve directly for theta, right? By way of this sort of pseudo-inverse multiplied by the outputs y, as shown in the normal equation method. But what if this is intractable, and why would it be intractable, right? Well, one of the reasons is the value x, in this case x, the matrix down below, is not just one entry, right? So every entry of our data, say we have a data set with 1,000 features or 10,000 features. So, for every house, you get 10,000 different things. For example, think about this even as like a mesh or some kind of information that is very high dimensional. And so say we have a million different kinds of entries of examples. We have a million data points, and each data point consists of 10,000 features. So this matrix X is going to be a million by 10,000. And so this calculation of the X transpose times itself is already a very large calculation, but then further taking the inverse of that may be an intractable computation. And that's going to be really, really problematic if we want to calculate this. So while there are techniques to directly solve for the values, right, and keep in mind y would also be a million length vector, because y represents for each x data point, we have a corresponding label for that data point. And so this calculation, this normal equation method, what we learned in kind of high school linear algebra or whatever, wherever we learned it, or like just in algebra, right, of solving a set of linear equations, may be an intractable calculation, or one that would just take way too much time given the hardware that we're running on. And so learning approaches this problem kind of in a different way. Instead of approaching it like this, what we do is we then instead, I'm not sure why this is impossible, but what we do then instead is we sample our x values. So instead of solving directly for our theta values, what we do is we say, okay, well, y hat is going to be equivalent to our prediction, y hat being a prediction for a particular sample, is going to be equivalent to this dot product to a particular sample of data from our x data set, and then we're going to kind of make a predictions for an arbitrary theta. So we're just going to choose a bunch of theta values, and the way that you choose them obviously matters, and we'll talk about that more later in the course. And now we have a bunch of y sort of predicted values. So we have our vector of y's that we know from our data set, and then we have a subsampling of y's that we've predicted based on a subsampling of x values. So instead of choosing all million x inputs, we've only done this for maybe 100 or 200 samples. And now what we can do is for each one of those 200 samples of that, what's called a mini batch, we can then calculate this error, or also what's called the loss. And the loss is essentially, in this case, we're using the L2 norm. And the L2 norm specifically is the Euclidean distance. And you're saying, wait, where's the Euclidean distance? There's no square root there. Well, the reason we don't do a square root is who cares? Because we're optimizing this loss function against that's parameterized by theta. And so what we do is for every single value that we've sampled, we have a prediction. And from that, so what we take is we take the correct label. So say I predicted dog, but the answer was cat, and those are just values, right? So you have 1 or 3, or, well, okay, this is a little bit not true. We're talking about linear regression here. So say the price of the house was 500 and I predicted 450, so the error here would be 50, and then you take it to the power of 2, and then we sum across that mini batch. So the total amount of loss that we have from a particular selection of theta values is going to be the average of those sort of L2 norm errors. And what now we want to do is we want to minimize that loss. So if we say, oh, on average, we're $45 away from the correct value across our data set. And if you can, and I'm not going to go too deep into this because we'll talk about this in later lectures about linear regression, but if I can figure out the derivative of the loss respective to each one of these theta values, then I can apply that derivative to the theta values and start to nudge our set of thetas in the correct direction. So it's almost like I have the error and I want to figure out the contribution to that error based on every single theta value that we've used to calculate our predictions. And so this sort of idea of having an algorithm, a model that produces a loss that's a representative of how far away are we from our intended outputs, and then taking that loss and then somehow applying that loss in a constructive way to our model such that our model is improving. That's the entire idea of learning. That's the entire idea of linear regression, which we'll go deeper into in the next lecture. But that's actually it. Machine learning, that's all machine learning is. All you're doing with machine learning is you're determining you're taking a model, you're applying it to a bunch of data, you're getting an output, your sort of a result. You're figuring out how far away is that result from what I want it to be. And what I want it to be is based on the data that you have. So again, you can't separate the model and the algorithm from the data, because the data literally defines the algorithm. As you can see, these algorithms are largely very simple linear models, like linear calculations, such as a dot product with a vector, except you do it a lot of times and with big numbers and big dimensions and stuff like that. But if you can kind of output what your intended target is, figure out how far it is from your intended goal, and then sort of apply that error to your model to keep nudging your model in the right direction, which is what we'll talk about in the future lectures. That's all learning is. That's all supervised learning is. And you can see how you can do this in one dimension relatively reasonably. And this generalizes to multiple dimensions very rapidly in linear and both logistic regression, as we'll talk about in the next sort of set of lectures. 1 second, I'm going to take a pause. Okay, so I'll keep this lecture going until the end of supervised learning, and then I'll split it up into 2 lectures to cover unsupervised and reinforcement learning in the next one, because we're already kind of deep into it. But let's talk about one of the major applications of supervised learning that's applicable to simulation and games in particular, and that's computer vision. And computer vision is not just limited to machine learning, but there are very, very exciting machine learning techniques to accomplish particular tasks in computer vision, which we'll cover a little bit here. And they break down into kind of 4 big ones, where the last one is sort of like more ambiguous. But the first one is classification. We already talked about this a little bit, where I give you an image and I want you to tell me what the image is. Maybe it's a cat, maybe it's a dog, maybe it's a plane, and what have you. There's also the subject of object detection and localization, which we'll talk about, which is basically asking you to tell me where in the image are there objects, and in the case of detection, not only where in the image are there objects, but what are those objects. So detection is kind of like a combination of localization and classification. There's segmentation, and segmentation is more of a pixel level thing, as we'll talk about, and then pose estimation and other regression tasks, which is sort of like I have an image, I have some regression-based information on it, such as like location of an object, and I want to regress that. And so it's kind of like the linear regression example, where you're kind of getting closer to a continuous value versus a classification and what have you, which we'll talk about as well. So let's talk about classification. Object classification is essentially taking an image and then telling you what's in it. So like in the bottom right corner, this is an example from ResNet, I believe. You take an image, you provide it to ResNet, and it gives you a 99.4% likelihood that this image is of a cat. This particular aspect of computer vision really saw a huge jump in 2012 by way of the introduction of AlexNet. And as you can see, that was sort of the beginning of the sort of deep learning revolution, where AlexNet introduced these convolutional neural networks, which we'll talk about a lot in this course. But what convolutional neural networks really are able to do is utilize spatial information in the image by way of parameter sharing. And AlexNet was one of the first, deeper networks with 8 layers, and was able to have this massive jump from 2011 to 2012 of almost 10% in the error. And the previous examples, the previous approaches were things we're using like histograms of oriented gradients And so we can talk about this more, and please let me know in the Discord if this is something that's of interest, and I'm happy to go deeper into it. But there are a lot of different approaches to computer vision that were kind of biologically based before AlexNet sort of threw away all of these opinionated approaches and instead replaced them with this sort of ambiguous network that learned to get better on its own without having to have us determine what each layer does. So in the case of histogram of oriented gradients, for example, you would take an image and sort of figure out all of the edges, and then based on those edges, apply things like a support vector machine or a linear regression task or a logistic regression task. And that wasn't quite as good, as we'll see in this course, for example, as letting a machine learning algorithm just learn what that histogram of oriented gradients solution should be. And we'll talk a lot about this in this course, in the sense that a lot of these computer vision algorithms, the first layers of them, in particular for convolutional neural networks, those first layers look a lot like what's called Gabor filters, which are the things that you would use to determine these oriented gradients, but they're not quite. And if you replace that first layer with Gabor filters, it doesn't quite work as well as letting the network learn those first layers. So it's a very interesting kind of result. And as you can see, from 2012 to 2015, with the introduction of ResNet, we're starting to see the error rate go to superhuman capability. So ResNet in 2015 resulted in a 3.57% error, top 1 error, I believe. And the difference between top 1 and top 5, as you can see, you have predictions for multiple things, and we also kind of evaluate these algorithms based on not just the top prediction, but the other ones. So for example, in this case, cat, tiger, and cougar kind of makes sense, and this algorithm would be better than one that would say cat, dog, and plane as the top 3 things. Even though it said cat is the number 1, this algorithm is better than one that suggests that the other option may be a something else, like a pipe or whatever. And the reason for that is some images have a little bit more context, right? Like imagine I gave you an image in real life that's sort of a 3-wheeled motorcycle, and so I would like the top 3 options to be car, motorcycle, and things like that, even though technically we don't have a tricycle or whatever it is in our data set. Classification, kind of the sort of bread and butter of computer vision machine learning algorithms. So moving on to sort of localization and detection, as we mentioned, localization is the task of determining where in an image an object is located, and the detection further takes localization and also wants to detect and classify what those objects are. So on the right here is an example of an algorithm called YOLO. This was a paper that was, I forget when it was, let me move myself here a little bit. Cool. So YOLO kind of introduced this idea of it almost like a clustering algorithm. So if you're familiar with clustered rendering, what you're doing is you're taking an image, splitting it up into regions, then you classify each region and kind of figure out, okay, this kind of looks like a dog, this kind of is a bike, this is whatever. Then you use also a separate approach to regress a bounding box for each one of those regions. And once you have sort of what's called proposed bounding boxes, you then utilizing the class probability map, as you can see below, you can then assign and determine which object is the most likely one by way of sort of what's called intersection over union techniques, as well as then looking into the class probability map and saying, okay, well, most likely we have a dog in this particular region. YOLO is one approach to this, and the reason it's called YOLO is it's like you only look once, so you only process the image one time, and that's why it's a very effective algorithm. It's very fast. There are other techniques. For example, AlexNet, when it was introduced in 2012, also demonstrated segmentation and detection localization, but it wasn't actually discussed how they did it, and so that came out later in a paper called Overfeet. And Overfeet kind of introduced the idea of a sliding window approach to this. We'll talk about why sliding window is kind of why you did it, because it was based on convolutional neural networks. And what all it did was basically take an image and slide the algorithm across it, and then using a lot of very similar techniques to YOLO, sort of combine potential bounding boxes and classifications to kind of come up with a detection and even segmentation thing, which we'll talk about in a minute. There are other techniques, another class of techniques called region proposal networks. such as faster RCNN and mask RCNN. And originally, it's funny, it started RCNN, or region proposal CNN, then fast RCNN, then faster RCNN, then mask RCNN, which is the current recent one. And the difference is what it does. The region proposal networks first start off with an algorithm that determines where in your image you likely have an object. So it actually splits the localization task from the detection task, because if you know where there are objects in an image, you can then run each one of those through a classification network to then sort of determine what objects those are. So there's a lot of different techniques here, but you can kind of see the value of this, right? Where I can give you an image and maybe different objects in there, and you can tell me, oh, there's a dog, a bike, and a car in this particular image. So moving on to segmentation. So segmentation is sort of like classification, but at a per pixel level. This introduced some really cool approaches, such as fully convolutional networks, because one of the unique things about segmentation is you have an image, right? And you basic, a lot of these courses we'll talk about sort of bottleneck it down to a feature representation of some kind, which doesn't look anything like your original image, but it has information about the image that represents different features, like, oh, this is all these features combined have something to do with a cat, dog, or what have you, right? So the difficult thing about segmentation is now you want to take that information, that feature representation of your input image, and then upscale it to an image as well, because the output of segmentation is an image the same size as the input image, right? It's just a bunch of colors, and those colors are not just colors, they're like values, they're like numbers. They represent the class of that particular object, be it a pole or a dog, a pedestrian, or a car. And so fully convolutional networks introduced, this was introduced, like, for example, UNet with skip connections, where you upscale that representation with generally strided deconvolutional stages with a skip connection that conditioned each one of those deconvolutional stages against the input at that same kind of representative thing. So you have these like mirrored, it almost kind of looks like a bottleneck, like an hourglass on its side. If this is something that's interesting to any of you in the class, please let me know, and I'm happy to go deeper on any of these subjects. As I mentioned in the first lecture, I'm on the perception team at Unity, and these are the things that we deal a lot in per the sort of ability to do a lot of these kind of computer vision tasks in doing this with synthetic data. Synthetic data is something that we're going to talk about a fair bit here, because as you can see in this image, right, our ground truth, remember, these are supervised learning techniques. So that means for every data image, we need a respective image with correct segmentation information. That means somebody had to sit there and draw for millions of images what color, like what class each one of these objects is. As you can hear, this is an error-prone process. This is a very tedious, time-consuming process. There are now a lot of public data sets that provide this, but again, as we mentioned, the algorithm is hard to separate from the data. So the ability to generate this data with, say, a graphics engine like Unity or Unreal or your own engine is one interesting way to approach building a lot of these systems. However, this presents a new issue, which is synthetic data is not real data, and there are differences. And this kind of introduces what's called the sim to real gap. And the sim to real gap is sort of that gap between synthetic data when you simulate to when you take it into the real world, and now all of a sudden your algorithm doesn't work quite as well as it did against your perfect graphics data, for example. So let's move on. We can talk a lot more about that if that's an interesting thing to you all in the class. Finally, on the supervised computer vision side, and I think after this I'll cut it off for the day. Or actually, no, never mind. Ignore I said that. We have also this concept of pose estimation and regression tasks. So one of the things that, for example, mask RCNN was able to show is if you provide these algorithms with also the pose, and the pose being, in this case, take a human being and take a picture of them and then draw on top of them these sort of key points of your shoulders, your head, your hands, and so on, you can actually build an algorithm that then will take an arbitrary image of a person and then tell you in what pose that they are in. You can imagine the applications for this for games, for example, is very, very interesting. Now, this is actually a form of a regression task, just like a bounding box or other things, but you can extend this to more general type of things as well. For example, face landmark detection and tracking. So say I give you a data set full of people's faces and where their eyes are, where their nose is, where all these key points about their jaw and their mouth. You can then generate an algorithm that can basically, given an arbitrary person's face, then output these locations, either in 2D or 3D. And if you've seen a lot of these Snapchat AR filters, where it's like face swap or what have you, that's the technology behind this. It's essentially these algorithms that have been trained to take a look at a face and then figure out the landmarks, those landmarks being eyes, nose, and what have you. And then what they do is they map that to some kind of effect, say, whatever makes your eyes bigger, or every time you open your mouth, a big thing explodes, whatever. But that's, how you can do this stuff. So, you might be asking yourself at this point, we talked a little bit about synthetic data already as a solution to this problem, but how can a network learn these arbitrary things? And as I mentioned, you need a lot of data, right? In the case of the face landmark stuff, you need a large data set with that annotated data that somebody has to sit there and map out. In fact, face landmark detection is a place where you see a lot of synthetic data being used and then fine-tuned, which we'll talk about later in the course, against real data, which is limited in nature. But this is kind of the bottleneck of a lot of supervised learning, is that you need a lot of data to generalize on a particular task. And if you don't have that data, you have to make it. And making it can take time and can cost money, or in some cases is just not even really possible in a reasonable degree. So the last thing we'll talk about with supervised machine learning is natural language processing. And natural language processing deals with data that is text or audio. Like, it's not usually talking about audio. What we do with audio and speech is first we do speech to text, which is a whole different subject, which I'm not going to talk about. But speech to text is also a supervised learning algorithm, generally speaking. But natural language processing generally deals with language at the level of text. So assume something has already given us the conversion from speech to text, or we're dealing with the internet and data in the internet or books or whatever. One of the main kind of algorithm tasks for supervised natural language processing is machine translation. So we have text in one language and we want to convert it into a different language. And also text generation, which is a semi-supervised or unsupervised process. For example, as in this image here from this really cool paper from OpenAI, what they did is they trained a recurrent neural network to process it like in a supervised fashion to understand text, to basically kind of predict the next word from text. So in that sense, it's a supervised algorithm because you're giving it its next word. But then they kind of dissected the algorithm a bit. They dissected the network to find a particular neuron that highlighted that the output of the neuron, meaning the activation value, or just this value that's coming out of this neuron, mapped directly to sort of the sentiment of the underlying text. So if you look at this, the green represents a positive area of text, whereas the red, represents kind of negative sentiment. And so this was sort of a interesting approach where they were able to kind of, in an unsupervised fashion, find these neurons that represented particular kinds of, underlying aspects of the data. But that algorithm was trained in a supervised fashion by way of ground truth, which, again, you can see where the lines blur between supervised and unsupervised learning. But first, let's talk about machine translation, which, again, I don't know why I'm not able to navigate this PDF. We're talking about machine learning, and then I can't even use a PDF. That's fine. Anyways, so with supervised machine learning, let's talk about translation. This is one of the most kind of appealing aspects of natural language processing. I give you some text in one language, and then the algorithm outputs text in another. The reason this is supervised is you need a corpus of text in your given language with accurate translation, which is maybe done by a human being in a different target language. And this is why it's supervised, because you essentially know the answer against a known piece of data. And if you can train an algorithm against that known data, then in theory, applying it to new data will give you the correct answer. And this is sort of what we do. Traditionally, this has been done with what's called recurrent network topologies, like LSTMs or vanilla RNNs and so on. But recently, with sort of the introduction of attention and multi-head attention and the transformer architecture, this has been done now with transformers. And you can see on the right side, this is sort of an example of why transformers are superior. And the reason is recurrent network topologies, and I can go as deep into natural language processing as you all want, so please let me know in the Discord if this is something you were interested in exploring further. It's very much a hot area of machine learning because so much of the world is in text and data like that. But one of the things that transformers can do by way of attention is they deal with the data all at once, whereas recurrent topologies deal with data one word or one character at a time. And it's very hard to retain memory over a very long period of recursive recurrent applications of a particular network. And in some cases, imagine a book where the name of the character of the book is only mentioned in the first page and then in the last page, right? There's a very long dependency there, and then a recurrent network will very quickly forget about that, whereas a transformer architecture, because it's dealing with the entire text sort of transformed in a positional encoding, can deal with it all at once. And you can see this in this image here from a transformer, because in some cases you have words that are in the beginning of the sentence that represents words at the end of the sentence. This is a translation from English to French? Spanish? I don't really know. I think it's French. But you can see in some cases words get kind of flipped around, and this is something that recurrent networks have a lot of trouble doing, even in that sort of short-term kind of sense. And then let's talk about supervised. Well, this is not actually supervised. So text generation is not exactly a supervised technique, although, like I mentioned before, it's generally trained on supervised data, although that's not true entirely. So this one's a bit of a sort of supervised, but not really. But we can actually use machine learning models to generate new text based on existing text. So in that sense, it's data, it's kind of unstructured, but it's kind of structured because we've chosen what to present it with. And again, this has been traditionally done with recurrent networks, either at the word recurrently applied to either a word or the character, but recently has moved towards transformer-based architectures, for example, GPT-3. You can see on the right here an example of a GPT-3 output. So the blue is human entered. So I would enter, "Dear human philosophers, I read your comments on my abilities and limitations with great interest." And the rest of the text is entirely generated by this model. You can see how this model is even kind of introspecting. It almost sounds like it knows that it's conscious, but even it says, "Am I conscious? No. Do I have a sense of morality? No. Am I intelligent? Yes." And it's very interesting what these things can do. We'll talk about kind of the limitations of GPT-3 and how it can do this stuff, which is great, but also where it's limited. So it's a very interesting kind of application, and this is a very applicable use case given games and the need to create dialogue and stuff like that. There's a lot of really interesting applications there. So I'm going to cut it off here, and I'm going to kick off the next portion of this lecture on and we'll start talking about unsupervised learning. So yeah, that's it for part 1 of lecture 2, and I'll see you in a moment.